This is going to be a third lecture in the series, a crash foundation course in mathematics. So in the first lecture we looked at quantifiers and combination sentences using conjunctions and or, and how to negate all of them, and the order of quantifiers, etc. In the second lecture we looked at how to define subsets, and the most important thing was how to define arbitrary union, what is meant by a family of sets, index family of subsets, and how to talk about their union and intersection, etc. And we also looked at one or two examples. And today we are going to talk about functions. As usual, I am going to assume you already know about functions definitions, so I am not going to spend much time on that. The crucial thing here in functions is the concept of inverse functions, inverse images. And unfortunately, it's not emphasized much, even though modern mathematics uses inverse images a lot, okay, because they obey well with respect to theoretic operations. But that's not emphasized, and the concept is not well introduced to the students. So that's my experience. So we will look at those things a little more carefully, and that will be the thing. Hopefully this should be about 45 minutes or so, but let's go. Right. Okay. Yeah. So, as I said, I am going to assume you already know what is meant by a function from a set x to y. So just to recall, for every x in capital X, you are given a unique y in capital Y, so that x takes to y. So this y is what we denote by fx. This stands for unique. All of you know this. This is read as unique. Okay? Alright. Therefore, this is a function. And just quickly recall, when do I say the function f is 1, 1? Or people are fond of something Latin words always f is injective. When do I say that? You give me x1 and x2 in the domain, and assume x1 is not equal to x2, then I want to say fx1 is not equal to fx2. Okay? There is also a contrapositive term. This is also part of logic. Suppose the statement P implies the statement Q, right? Then that is the truth of P implies truth of Q. And therefore, if I take the Q negation, then if Q negation is true, then I want to say P negation is true. This is what is called contrapositive. Okay? Don't think about if these things confuse, don't worry about it, okay? But try to understand in the context. So, because when I want to say a function f is 1, 1, most often this is the trick you do. Assume x1 and x2 are given in x, and such that fx1 equal to fx2, then I will prove x1 equal to x2. You understand that? So these two conditions are the same. This one, call it star, and this one, call it double star. These two are the same, equivalent statement. Quickly go understand this. Yeah? So if f is 1, 1, that means if x1 is not equal to fx1 is not equal to fx2. Then I want to say this condition is satisfied. Alright? Suppose I have x1 and x2 so that fx1 equal to fx2. Then I want to say x1 is not equal to x2. I am assuming f is 1, 1. You understand that? Okay. Suppose x1 is not equal to x2, then since f is 1, 1, I know fx1 is not equal to fx2. Do you follow that? If f is 1, 1, then I claim this. Okay, this hypothesis, x1 and x2 are in x and fx1 equal to fx2, should imply x1 equal to x2. This is the hypothesis. This should imply this statement. This is the hypothesis. This is the conclusion. Okay. Don't worry about these things. Just get used to this way of thinking so that you will feel more comfortable. Okay. Right. Are you following? So I am assuming f is 1, 1. If x1, x2 are given, so that fx1 equal to fx2, okay. Then I want to say x1 must be equal to x2. Okay. How do I know that? Because if suppose x1 is not equal to x2, then since f is 1, 1, then I know fx1 cannot be fx2, but that's a contradiction to my hypothesis. Do you understand? Now converse. Let's assume f is a function with this property. What is the property? x1 and x2 are in x, so that whenever fx1 is fx2, I can conclude x1 is fx2. Then I want to prove f is 1, 1. Okay? Right. Suppose f is not 1, 1. What does that mean? Whenever you give me x1, x2, so that x1 is not equal to x2, this is for every choice of x1, x2, so that x1 is not equal to x2, fx1 is not equal to fx2. I want to prove that. Suppose f is not 1, 1. What does that mean? That means there exists x1, x2, so that x1 is not equal to x2. But fx1 equal to fx2. You understand that? Yeah? Okay. But what is the hypothesis about my function? Whenever x1, x2 are there, so that fx1 equal to fx2, then necessarily x1 equal to x2. But that's a contradiction because I start with x1 not equal to x2. Okay? Please go through that. As I said, if you have any problem, you should consult the reference. Okay, this is one. Next thing is f is onto. Again, many people use the so-called notion of pre-image, etc. Usually I don't use it. It's yet another jargon, but you should know what I want to prove. If f is x to y, then it's best to say it's onto. This we did already on the first lecture, when if for every y in y has some property. What is the property? I can find an x. There is an x. So that what happens? Y equal to fx. You understand that? So I have a y, then I can always find an x, so that f takes x to y. Okay, there may be more than one x, but at least I have to say there is x. You understand? This yix is what you call a pre-image, etc. But I don't need such words. Okay, right. So when f is not onto, this also we saw already. That means there is a y. So I can find a y. Okay, so that whatever x you give me, all of them will go somewhere, but they will not hit y. Okay, they will not hit y. There is a y, so that for every x in capital X, y cannot be equal to fx. Okay, all these things you have seen. Okay, right. Now I want you, again, this is also we have done in the first lecture, I believe, no, in the second lecture on subsets. Suppose A is a subset of X, then we define what is f of A. Do you remember that? This is a subset of X. How did I define? Okay, again look at the picture. This is my A, and this is my Y, this is my F, and f of A is this. What does it mean? Start with any X, collect all the images fx. So how do I write it? Mathematical precise way. It is set of all y. So do you remember how do you define a subset? F of A must be a subset of y. Then therefore I have to tell, if you give me a y in capital Y, I have to tell you when y belongs to f of A. When does y belong to f of A? There is x. Where? In A. Okay? So that y equal to fx. Okay, loosely this is what you say. Fx, collect all the images as x varies over A. Okay? Do all of you understand this? Okay. Right. So let us just make use of the concepts which you have learned. Okay, just to do only one thing. Suppose AI is a family, indexed family of subsets in X. So this is okay. Then we had already defined union AI, I in I. How did we define? This is set of all X and capital X. With what property? There is at least one J in I, so that X belongs to AJ. That is, collect all elements which is at least one AI. If you want, you can also write I, but I am just writing this. Okay. Then what I want to claim? I want to claim f of union AI, I in I is equal to union f of AI. Okay. For example, these are the things which you would not have seen, even though you may be using in your courses. You may not have really gone through a proof. Okay, let us go through it quickly, right? So I want to say this set equal to this set. So when I say two sets are equal, what do I have to do? I have to start with, let's say, each is a subset of the other. So let us start with the left hand side. So start with an element y. I have to prove y belong to this. Right? Let us do that. So y belong to f of union ai. What is the meaning? This means there exists x where in union ai. Okay, I am not writing I in I. Okay, so that y equal to x. You right? But what does it mean to say there exists an x in union ai? That means there exists a j in I, so that x belong to aj and y equal to f of x. You follow that? I am just using our definition of union. But what does this mean? This means x belong to f of aj. Right? Sorry, y belong to f of aj. Because y equal to fx, where x is in aj. Therefore, y belong to aj. But then this implies y belong to union f of a. I in I. Right? Because you had already seen, recall, union ai, if I take, and j is an element of I, then aj is contained in this. Here it's not ai, it's f of ai. Right? So what I have shown? I have shown that f of union ai is a subset of union f of ai. Right? Now we have to prove the converse. So let's start with the y here. So y belong to union f of ai. What does that mean? There is a j, so that y belong to f of aj. What does that mean? That means there exists j and x in aj, so that y equal to f of x. Right? Is that clear? Therefore, this implies x belong to union ai, because x belong to aj and aj is a subset of union ai. Therefore, x belong to a, and so that y equal to f of x. But what does this mean? This means y belong to f of union ai, because there is an x in the union, so that y equal to fx. That means y belong to f of a. So pause, review, proceed. Okay. So we had already done a bit. These kind of things, just go through once or twice. That's it. You will feel very comfortable. This is nothing very kind of deeper or anything. It just uses the definition. Unfortunately, these things are not taught. Okay, they are glossed over in the typical courses. Teachers think that they are all easy, or the students know how to do that. But you should learn how to write a rigorous proof. That's what we did. But unfortunately, this f of a, let us give a name. I don't know whether I give an image of a under f, under the function f. One also calls it direct image, because of what we are going to say later, direct image. Okay, but forget it. Image of a under the function f. Okay. Now, therefore, taking images under the function, it behaves well with respect to union. That is, f of union will be equal to union of the images, right? That is, image of union equal to union of images. This is what you are saying. Okay, this is a kind of quick mnemonic way of understanding what we did, right? F of union ai equal to union of f of ai. That's what we have done. But you can ask whether is it the same as intersection. That is, if I take a and b in A, okay, is f of a intersection b is a subset of equal to f of a intersection f of b. Okay, you will see this is always true. This is very easy. Okay, check it. Because if x belong to y belong to this, there is x in a intersection b, so that y equal to fx. Since x is in A intersection B, y belong to FA and y belong to FB, therefore y belong to FA intersection FB. Therefore, I actually checked it for you. Yeah, are you happy? But this way is not true. One can figure it out, take some time to figure it out what happens, what goes wrong. But let me just look at a very trivial example. Suppose A and B are non-empty disjoint sets, and suppose F is, these are non-empty, this is not empty, this is also not empty. And suppose F is x to y and A and B are subsets of x, and suppose F is a constant function. That is f of is equal to, that is a y naught for all x in capital X. Then what is f of a? Remember, a is non-empty, therefore f of a will be singleton y naught. What is f of b? That is again, b is non-empty, therefore that will also be singleton y naught. Therefore f of a intersection f of b will be singleton y naught. But what is a intersection b? F of a intersection b? That is empty. Why? Do you understand this? Why this is true? That is, this is f of empty set. Okay, f of empty set will be subset of y. Okay, I claim this is nothing other than empty set. Why? Because the moment you say there is a y here, what is the definition? That means there exists x in the empty set, so that y equal to fx. But there is no such x because empty set. Therefore, there is no y which can be a member of f of empty set. Therefore, image of empty set is empty set. You follow that? And from that we conclude f of a intersection b can be a proper subset of f of a intersection f of b. In particular, equality may not hold. Okay? Take some time, go through this, pause, review and then proceed. Okay. But if f is 1, 1, then we have f of a intersection b is f of a intersection f of b. Okay? I'll just give a proof because sometimes this is required in mathematics. When f is 1, 1, this always happens. Even, okay? Let us go through the proof. So what do I have to do? We had already done this. Do you remember? So I only have to prove this one. So let y belong to f of a intersection f of b. What does that mean? This means there exists an a in capital A, so that y equal to f of a. Similarly, there exists a b in capital B, so that y equal to f of b. Do you understand that? Yeah. But what do I know? If f is 1, 1, I have f of a equal to f of b. Therefore, this, since f is 1, 1, this implies a must be equal to b. But a is in a, b is in b. That means this, call this as a common element x. This is an element of a intersection. Right? Therefore, x, the common element, belong to a intersection b, and y equal to fx. That means y belong to f of a intersection b. So how do you think I have proved? I start with the y in f a intersection fb, then I proved there is an x in a intersection b, so that y equal to fx. That means these two are equal. This is under the assumption f is 1. Right? Do you think this is just to make sure that you understand this kind of question? Okay? This kind of proof. Suppose I have, is it true if f is 1, 1? Okay? F of intersection ai is same as intersection f of ai. Okay? If you want, you can pause and review and, okay, just to make sure that you understand this logic which we just now learned, try to imitate that kind of logic and see whether you can prove it. Yeah? You follow what I'm saying? That will be a good thing so that you also understand, you also see whether this result generalizes to a more general setup. Okay? Okay. Now, we are going to talk about the next important concept. Let me just check how much time I have. Now we are going to talk about the next important concept of inverse images. So the problem here is I have a function f from x to y. Okay. For direct images, what did I start with? I started with a subset A of x, and then I created a subset fa, a subset of y. Now we want to do the other arrow. What do you think I should do? Yes. So let us look at a picture. So let me write it. So this is my x, and this may be my y, and this is my b. Okay. What I am looking at is the set of. This is what I am going to denote by f inverse b. Okay. So what is that? I am going to define that. So f inverse b, this is a subset of x. Therefore, I have to tell you, give me an element x in x when x is going to be in f inverse b. Okay, don't use the pre-image etc. Get confused. It's utterly simple. I am going to say and give me an element x here. I want to know when it is going to be in f inverse b. It should not be written like this. It should be here, right? I have to say when does it happen? If and only if fx is in b. That's it. So look at each element y and look at any x so that x gets mapped to this y. It could be any y. You follow that? But don't worry, just think of this one. So when I give a point, let us say x dash in x, when I say x dash is not in f inverse b, what does that mean? That means fx dash is not in b. That's it. Right? And x is in f inverse b. What does that mean? It means fx is in b. Do you follow that? Please go through that. Okay? Internalize that. Okay? You should not just stand as a statement. You should begin to imagine. So, the moment you give me an x, okay? The moment you give me an x, I want to know whether it's going to be here or whether it's going to be here. How will I know that? Look at the image of x under f. If it is in b, yes, it is in this. Okay? Look at the image of x. If it is going to be here, my fx lies here but not in b, then this particular x is not going to be in my f inverse. Okay, do you understand? Take some time, internalize this. We will look at very simple examples so that you understand these concepts very well. Okay, right. So let us look at some examples, because this is a concept which is very much needed in modern mathematics. So we will give some at least 2 or 3 examples and then stop with the set theoretic operations. That is, inverse images behave well with respect to set theoretic operation. Yeah, by the way, I should tell you how I read this. F inverse b, I read it. This is, I will read it if you want. Inverse image of b under the function u. See? The first thing you should notice is, even though I write f inverse, you will notice that f is any function. Okay? F is any function. Not necessarily 1, 1, on 2, etc. Okay? I forgot to mention about 1, 1, on 2, and it has if it is a bijection, then it has the inverse y, f inverse from y to x. I hope all of you know that. If necessary, I will repeat. But at present, don't worry. Okay? This is any function. Therefore, this is a very bad symbol. So, we are not thinking of something like f inverse. Okay? This may or may not exist, because f is arbitrary. Do you follow that? Keep that in mind. That is why you have to say this is the inverse image of b under the function f. It's a very bad notation. Sometimes some people write like this. Okay, so that you don't confuse with the f inverse. Okay, but unfortunately this is a standard notation, so we will stick to that. Okay. Okay, let's look at the simplest example. Suppose f is a function from x to y which is constant again. So f of x equal to y naught for all x, capital X. Right? Now let us look at this. This is my b. Okay? And this is my b. This may be my b. Okay? My y naught may be this. You understand this? So this may be a b, this may be a b, this may be a b. Now I want to know what is f inverse of b. Right? Are you following? Now when does x belong to f inverse of b? If and only if. These are you have to remember. When you want to do the inverse images, don't worry about the word pre-image, etc., etc. Just look at x is in f inverse b if and only if fx is in b. But what is fx? That is y naught. Right? So what do you get? Think. So if y naught is not in b, then f inverse b must be empty. Do you see that? Yeah, because if x belongs to f inverse b, if you say x belongs to f inverse b, that means fx must be in b, but fx is y naught, therefore y naught is in b. But your assumption is y naught is not in b. Therefore, you understand. Okay? Pause, review, proceed. Conversely, if y naught is in b, what is f inverse b? Can you guess? What is the question I have to ask? Start with an x in S when x belongs to f inverse b. Alright? What is f of x? F of x is y naught. Does y naught belong to b? Yes. Therefore, what does it mean? Give me any x in x. Okay? Then that x belongs to b. That is every x belongs to b. Therefore, this means f inverse of b must be all of x. Do you follow that? Am I going too fast? So start with y naught in b. I want to know whether x is in f inverse of b. Give me any element x. Then what is fx? That is y naught. Right? Fx is y naught. Does y naught belong to b? Yes. That's my assumption. Therefore x belongs to f inverse b. Right? You understand? Because if x belongs to f inverse b, if only if fx belongs to b. But that's correct. Y naught. That is y naught. That belongs to b. Okay? Therefore, what is that you have found? You have found that for any subset b, this is equal to empty set if y naught is not in x. Oh, sorry, y naught is not in b. And equal to all of x if y naught is in b. Okay? Take some time, go through this, pause, proceed, and then pause, review, and then proceed. Let us look at example 2 now. Okay. Suppose I have f from R to R. This is my favorite example at the BSc level, usually. And f of x equal to x squared. Right? Now suppose my set B, which is a subset of the codomain B, is a singleton 4. Then what is f inverse of B? What is the question I have to ask? Start with a real number x in the domain. When does x belong to this? X belongs to f inverse b if and only if fx belongs to b. But what is fx? That is x squared. Okay, that belongs to b. That is, it belongs to 4. That is if and only if x squared equal to 4. So what are the real numbers such that x squared equal to 4? They are plus or minus 2. Therefore, f inverse of singleton 4 is plus or minus 2. Do you follow that? Yeah? Right. Now suppose I say there is a subset B of R, this is a codomain. Okay? That's such that f inverse of B is empty. What can you conclude? Is the question clear? Suppose I give a subset B of R and the function f is f of x equal to x squared, I say f inverse of b is empty. What can you conclude about b? Let us go through that. That means what? I have an x. Give me any real number x. Okay, given any x. So when I write for all x, this means given any x in R, x is not in f inverse b. You understand that? Yeah. But this is the same as saying we had already seen. That means fx is not in b. But what does that mean? X squared is not in b. Right? Now, this is the example which I wanted to do yesterday about subsets. I forgot. Okay, that would be better. So anyway, it doesn't matter. Now, what do I know? Given any real number x in R, what do I know about x squared? I know it's always greater than or equal to 0. Right? Therefore, okay, in some sense this implies no non-negative real number can be in B. Do you understand that? Suppose alpha is non-negative, okay, from real analysis we already know there is an x, a real number, so that x squared equal to alpha. Right? Square root exists for non-negative real numbers. You understand? Right? Are you following? Okay. Now, so what do I claim? Therefore, if I claim no non-negative real number alpha can be an element of B, this cannot happen. Why? Suppose this happened, then there is a real number x, so that x squared equal to alpha. You understand that? Right? See, therefore, that x, that is, if you want to call it, think of it square root of alpha plus or minus, but anyway square root of alpha. Therefore, square root of alpha is my x, then f of x is alpha, that is in B, therefore B is not empty. A contradiction. Yeah? I want you to think, no, don't look for a neat proof for anything. Think. So, what you have shown is, if B is, f inverse of B is empty, then B cannot have any non-negative real number. Therefore, B must be a subset of and you can see this also converse. Okay, check. Yeah? Let us look at one more example in the same thing. Now suppose my B is let us say yeah, this example I want to do yesterday. I don't remember whether I did that. Okay, suppose B is from 9 to 16. Right? Now what is f inverse B? So I have 0, I have minus 9, I have 16 here. Yeah? What is the first thing you notice that? See, if x is in f inverse B, okay, my fx is always greater than or equal to 0. Right? Are you following? Therefore, f inverse B is same as f inverse of 0 to 16. How many of you see this? Because if I start with any y here, which is in B, minus 9 up to 0 open, that is minus 9 to 0 open. If I take any y, there is no x such that fx equal to y. Just now we saw that. Do you follow that? Yeah? Therefore, this is the same thing. Therefore, what is the question I am asking? Give me a real number x in R such that fx, okay, x belong to f inverse B, which is same as f inverse of this 0 to 16. That happens if only if fx belongs to 0 to 16. Where does that happen? There is an obvious thing. Fx is x squared. X squared must be in 0 to 16. So, if I take 0 to 4 and similarly I take minus 4, all of them will be there. You understand? If only x belongs to minus 4 to plus 4. That is F inverse of minus 9 to 16 is same as the interval minus 1 to plus 3. Okay? This is just an example so that you get used to it. Yeah? If you want some geometry example, let us quickly look at. Suppose I have f from R2 to R such that fx, y equal to x. Yeah? So I have this. Okay? It goes here, right? It gets projected to this point, right? This is xy. You understand that? Now suppose my b is, let us say, minus 1 to plus 1. Okay, what is F inverse b? Notice that this is a subset of R2. So give me a point xy in R2. I want to know when is F inverse xy belong to F inverse b. This is if and only if fx belong to b. Yeah, sorry, f of xy belong to b. Right? But what is f of xy? F of xy is x belong to b. What is x? That is the first coordinate, x coordinate of the point xy. Right? It must be in b. What does it mean? b is minus 1 to plus 1. Therefore, it should lie in the interval. Therefore, you can see that is this set. Minus 1 to plus 1, all these points. Okay, including all the points whose x coordinate lie in the interval minus 1 to plus 1. Therefore, y can be anything. You follow that? Therefore, I find F inverse b is nothing other than subset of xy in R2 so that minus 1 less than or equal to x less than or equal to plus 1. That's it. That is the entire vertical strip, the closed vertical strip, that is going to be F inverse b. Okay? Lot more examples can be given, but as I said, you should refer to the book I referred to. That's enough. So, P R A. Now let's look at, we want to show inverse images behave well with respect to set theoretic operations. This is the very crucial fact. Okay? So what does it mean? We already saw direct images behave well with respect to union, but with respect to intersection, it does not behave well. We did not check about the complement. Okay? Now let's go through that. What we want to show is the following. Okay, f is a function from x to y, and bi is a family, indexed family of subsets in y. Then what do I know? I can make union bi. Call it as b. This is a subset of y. Then therefore it makes sense for me to talk about f inverse of b, which is f inverse of union bi. I in I. This I will not write I in I. Okay. Now what do you think I should guess? I said it behaves well. So what is your guess? We want to prove whether it's equal to union f inverse of bi. Notice that this is a subset of y, therefore f inverse of that, this will be subset of x, and for each bi it's subset of y, therefore f inverse bi will be subset of x, therefore the union will be subset of x. I want to say these two subsets are equal. Please internalize, understand this. So we want to prove this. That is what I want to prove. I want to prove F inverse of union Bi equal to union F inverse of Bi. Okay, so let us prove this way. So this is subset of x. Therefore, what should I say? Let x be in the here F inverse of union Bi. Right? I want to know whether x belongs to union F inverse of Bi. You follow that? Okay. Now, what does this mean? This is if and only if fx belongs to union Bi. Right? That means, when does fx belong to union Bi? That means there exists a j in I such that fx belongs to Bj. Go slow. Yeah? But fx belongs to Bj. What is the meaning of this? That means x belongs to F inverse of Bj. Where is j? J is in I. For some j, right? There is a j such that this happens. Right? Now, since x belongs to F inverse of Bj, what does that mean? X belongs to union F inverse of Bi. I in I. Because F inverse of Bj is one of these sets. Therefore, x belongs to B. So, do you think I have proved x belongs to F inverse of union implies x belongs to union of F inverse? Have you understood? Okay. In all these things, don't assume. When I say PRP, stop it, take a pen and paper and check it, or do it in your mind. Or you will see that you can do it. It's not difficult. Now let's look at the converse. So x belongs to union F inverse Bi. I want to know whether that means x belongs to F inverse union Bi. Yeah, that's a reverse inclusion. Again, exactly the same proof. X belongs to this. What does this imply? This means fx. Okay. Oh, sorry. X, there is a j, so that x belongs to F inverse of Bj. Right? It belongs to union of F inverse Bi. These are all subsets. Call them as Ai. X belongs to union Ai. That means x belongs to Aj for some j at least. Some j? Okay. Okay. This means what? Yeah. So x belongs to F inverse of Bj. Therefore, this means x belongs to union of F inverse of Bi. Because F inverse of Bj is one of these elements. Oh, sorry. Just see, I got carried away. This up to this what I said is correct, but I just want to do it slightly differently. Oh, again it's crashed. Okay, so let x belong to F inverse union F inverse Bi. This means x belong, there is a j in I, so that x belongs to F inverse of Bj. That means there is a j in I, right, so that fx belongs to Bj. Right? This means fx belongs to union Bi. Because Bj is an element. Okay, this means x belongs to F inverse of union Bi. That's what we wanted to prove. Okay, pause, we will proceed. So in a typical classroom, I will go a little more slow, but now you have the added advantage. There you can't stop me, here you can stop me. You can just pause the video, rewind it and play it, understand. Okay, this is the advantage here. So make use of this, exploit this, okay, facility which you may not have in a typical classroom. If you didn't understand, you can't stop me, right? Many students don't. Here you can do that. So we have proved equality. So similarly intersection. So What we want to prove is F inverse intersection Bi is same as intersection F inverse Bi. Okay, again the same thing. Let x belong to this. That means this implies Fx belong to intersection Bi. Okay, this implies Fx belong to Bi for all I, right? This implies x belong to F inverse of Bi for all I. Yeah, Fx belong to Bi if only x belong to. This actually these are all if only, but I am writing it only. Okay, this means x belong to intersection F inverse of Bi. Because x belong to F inverse of Bi for all I, that means x is a common element for each other subsets F inverse of Bi. That means it belongs to the intersection. Do you understand? Now you can see it's all if only. If x belong to intersection Bi, okay, then x belong to F inverse of Bi for each I. But that means Fx belong to Bi for each I. That means Fx belong to intersection Bi for all I, because Fx belong to Bi, therefore Fx belong to intersection Bi. That means there, okay, this x belong to F inverse of intersection Bi. So we prove this. Okay, pause, review and proceed. So we are ready for the last one. Now the last one is, suppose B is a subset of Y, then I can construct a set Y minus B. This is also a subset of Y, the complement, right? Okay. Now I can look for F inverse of BC. That is the subset of X. So just to have a picture, this is my Y, this is my B, this is my B complement. Right? I am looking for X. Okay, this is my, I am just drawing a picture, but this may not, okay, F inverse B. Pull back. Okay, the inverse image. What I want to do is, can you guess what I want to show? F inverse B, this is a subset of X, right? This is X. This is a subset of X. Therefore, take its complement, that is X minus this. I want to say this is nothing other than F inverse of Y minus B. If you feel comfortable with this, this is same as F inverse of B complement is F inverse of B complement. Okay? Inverse images behave well with respect to complements. Do you understand this? This is F inverse B. Therefore, what I want to claim, this is F inverse B complement. But what I want to say, this is equal to F inverse of this object. You follow that? Proof is again as usual trivial. Okay. Let us go through that. Suppose X is in X minus F inverse of B. I want to prove X belong to this side. If X belong to this, what does it mean? X belong to X, but X is same as saying X is not in F inverse B. Yeah? If X is not in F inverse B, we know this has happened if and only if Fx is not in B. Right? You follow that? Okay. So what does it mean? If Fx is not in B, yeah? So I start with an X here. I want to prove X is here. Right? To prove X is here, what does it mean? This is same as saying, okay, Fx belongs to Y minus B. Why Fx must be in Y? Because F is a function from X to Y, therefore it must also always be an element of Y. It's not in B, that's what I'm writing. This part, what does it mean? This means X belongs to F inverse of Y minus B. Y complement B. Do you understand this? lecture. Okay, start with x in x but not in f inverse of b. This happens if only if x is not in f inverse b. That we know now. When does this happen? This happens if only if x is not in b. Right? Therefore, that means what? Fx is in y but not in b. But that is equivalent to saying x is in f inverse of y. Therefore, we have proved these are equal. Yeah? I hope all of you understood, and at least some 40%. Okay, since I went fast, okay, it may be a little overwhelming with the notation, etc. But as I said, this whatever the 45-minute lectures I have given, if you stop at each PRP and review, it may take about 1 hour 15 minutes to 1 hour 30 minutes. By then you will be more comfortable. Okay, if you simply watch the videos like the way you watch a serial, of course you will still lack confidence. Yeah, please watch again, because these are the things which will be very much needed, okay, in your higher studies of mathematics. Unfortunately, as I said in my first or second lecture, teachers assume students already know functions and sets, so they don't spend time on these things, covering these basics. Okay, right, now we are done it. I hope you appreciate that. You will begin to enjoy your math classes. Okay, so have a good day, take care, stay safe.